Hello, my name is Braden Tisdale, and I'm part of the Bonsai Laboratory at Auburn University. Alongside my co-authors Deacon, Dr. Aaron Scott Pope, and Dr. Daniel Tauritz, I'm here to present our paper, Directing Evolution, the Automated Design of Evolutionary Pathways Using Directed Graphs. So what we're doing here is meta-optimization, and you've also heard this referred to as parameter tuning, and it's essentially just tuning an optimizer with an optimizer, as you can see here. Now this is required if you want a good EA, so we've all done this, I'm sure we're all familiar. And we're all familiar with the drawbacks. You know, there are a lot of different parameters that are interdependent and unpredictable, and evaluating their impacts on the EA is extremely costly. As a result of it being so important but also difficult, there are a lot of different methods that have been invented, as you can see here, from manual stuff to meta EAs to other software packages. Now imagine I hand you a pen and I want you to draw me what an EA looks like. You're almost certainly going to come up with something similar to this. This just describes pretty much every EA, and that's a problem from an optimization standpoint because there's not a whole lot that you can change here. The structure is very much set in stone. Now there are a lot of good reasons we use this specific structure, but empirical performance isn't one of them. No one's really done a serious analysis of that compared to other abstract forms. And if you think about the stuff you're actually allowed to change, you're really just swapping in and out these three operators, initialization, selection, and reproduction, and changing some of their parameters around, but you're not doing a whole lot else. And so we want to break away from that constraint and open up the structure as something that could be optimized. And so we would say that anything with these three operators that can pass individuals between them in a coherent way could be an EA. And in fact, for any given problem, could be a better EA than this traditional cycle. Now, despite this being so important, there's not actually been a whole lot of research done in this domain, but some early work in 2003 came up with a representation like this, and as you can see, every operator is assigned to an explicit individual in the population. Now, as you can imagine, this scales terribly, and at the end, their EAs had hundreds of operators within them. Now, some later follow-up work tried to throw this inside of a loop, and that did solve the bloat problem, but you still have issues with this explicit indexing, in that it doesn't let you coherently describe a large population in any kind of reasonable way. More recently, in 2013, attempts were made to solve this problem with TreeGP. Now, TreeGP has a lot of benefits and trade-offs, and the big issue here is that your representation is just limited by the structure of the tree. You can only pass individuals up, and you can never really split the population into multiple paths from a single point. You can only go to one operator. This work tried to mitigate these problems by adding a primitive that would save their input and make that available to terminals in future generations, and you can kind of see that here. It's essentially a way of passing individuals like this. Unfortunately, as far as we could tell, this was never actually utilized in any of the top-performing trees, and we hypothesized that that's due to difficulty in evolving an EA that actually benefits from this inclusion. For lack of a better word, it's simply too finicky. We want something that's more natural and easy to evolve. So to try and fix these problems, we thought back to the way that EAs were illustrated, as directed graphs like we saw earlier. Now they're illustrated that way because that does a very good job of representing the flow of individuals between the operations in a natural, coherent way. And so that's what we went with. We came up with a directed graph representation. And in our final representation, this is what a mu plus lambda evolutionary cycle would look like. And as you can see, it's a little more complex than the cycle we saw earlier, despite representing the same thing. And there are a lot of numbers and moving parts here that you're probably not familiar with, but we're going to take a few slides to go into detail on how this works. Now, at its most fundamental level, our representation is actually just a simple linear sequence of operations, and that's what these numbers here at the top of the vertices represent. That's their order of execution. As you would imagine, you start at 0, then 1, then 2, then back to 0, 1, 2, repeat, repeat, repeat until you terminate. Now, the way that individuals flow across the edges is, so imagine 1 is about to execute and 0 is already finished. There are individuals here that are 0's output, and then 1 pulls them in, does its operation, sends its individuals out to 2, where they'll wait for 2 to start executing, and that works fine. But there's a special consideration for when you have backwards edges. If you imagine the first pass, the first generation, well, 2's actually never executed, so when 0 looks here to find its individuals, its input, there's actually nothing there. So that's where we find our initial population. Backwards edges, the first pass, serves initialization. And that's analogous to the way that things are handled in the traditional cycle. You just don't typically have to think about it in this sort of abstract way. Now let's take a moment and discuss the way these vertices actually execute. When you have a vertex, you have your input edges and output edges, and we'll just say the sizes of these are A, B, X, Y, Z. That's the same thing as your mu here or your lambda here. The semicolon and index describe the order in which individuals are sent out. You'll have to read the paper to understand the implications of that. Now there's a very critical problem here. If your input sizes A plus B are bigger than your output sizes X plus Y plus Z, you're going to be removing individuals from the population no matter what. You're doing survival selection. But if the opposite is true, you're going to be adding individuals, reproduction. So to accommodate for this, we actually encode both of these operators in the vertex, and whichever one executes depends on these sizes. Survival selection in the one case, and parent selection in the other, or parent selection and reproduction in the other. Now there are some drawbacks to this approach, and there are also probably some alternatives, but we chose this because it allows for any vertex to be valid in any context. Now what we just discussed are actually what we have termed operator vertices, as opposed to mutator vertices. We don't really have time to delve into mutators too much, but shortly, they never change population size. Their output edges, for this reason, have percentage-based weights, not prescribed values, and they'll always sum to 100%. So now that we understand the way the graph functions, how do we actually evolve it? Well, recall that at its most basic, our representation is just a linear vector. And so we do a pretty simple crossover operation. But these vectors are of variable lengths, so we had to do a little more effort. And that involves sampling a value of alpha, which describes essentially the proportions that you're taking from each parent. And for example, we'll say here alpha is 0.5, and in that case the crossover points are in the dead center of each parent. If alpha was bigger, you'd take more from the first parent and less from the second parent. And if alpha was smaller, you'd take less from the first parent and more from the second parent. So we copied these pieces over. And of course there are also edges involved, and if these edges are fully contained within the pieces that you've taken, you just copy those over, of course. Other edges that aren't fully contained in these pieces are discarded, with one exception. If you have an edge that has the same endpoints in each parent, for example, from 3 to 1 in both parents, then we add that to the child. We take it randomly from either of the parents. And that produces a pretty simple output. The only caveat is that the indices of the second parent's contribution might shift up or down because the size of the first parent's contribution doesn't line up with the size of the second parent's crossover point, if that's understandable, if I explain that properly. But otherwise, it's pretty simple. So to empirically evaluate the performance of our optimization process, we wanted to use a benchmark, and we chose separable rastrogen. We used the Bebob test suite, very well-known benchmarking suite for optimization algorithms. Our goal here, our function, was ultimately to find an EA that, on average, solves three-dimensional separable rastrogen in the fewest number of evaluations. Per Bebob convention, when you solve the function when you get a function output of less than 10 to the negative 8. Importantly, you have to run each candidate EA independently several times to completion to get a good sample of its performance on average. And when you do this, you also need to generate a new random optimum for the function for each run for each EA. And here you can see the progress of optimization. X-axis is generations, and Y-axis is the average number of function evaluations required to solve the function for the best EA found in each run. And these are box plots because we did several runs, and this just shows their distributions. Now, the blue line is our adaptive mutation rate. We didn't have time to go into the mutation operator or the adaptivity algorithm, but essentially the fact that it goes down to a hard-coded minimum very rapidly indicates that our mutation operator was probably doing a terrible job and did not improve fitness ever. So that's not good. Also, we had a very aggressive policy of killing runs quickly early on if they didn't find a good EA quickly enough, because these are so computationally expensive. As you can see in the bottom left, by the 5th or 6th generation, we'd killed 90% of our runs. That's super aggressive, and that probably contributes a lot to some of this rapid improvements in fitness you see in the first few generations. But as you can see here, the optimization is not an illusion. There's an actual curve here. There's actual optimization going on. So things are looking good. Now, to serve as a basis for comparison, we used iRace to tune a traditional mu plus lambda EA. iRace is a pretty popular and highly regarded optimization tool designed specifically for parameter tuning. We ran it to completion 10 independent times and then ran it an 11th time using the first 10 runs winners as seeds. That's ad hoc. That doesn't necessarily have any basis in literature, but we thought it was a good way to ensure that iRace had the best chance possible to find the best EA that it could. As a benefit, this process used a comparable amount of processing time as our experimental optimizer, with each taking around 1,500 CPU hours to get the final results. That's certainly expensive, but it's still in the realm of reason if you want the absolute best EA that you can possibly get for a given problem. That's just under 2 days on 32 cores. So we took the best graphical EA found by our optimizer and the best traditional EA found by iRace, and we ran them on a series of benchmarks from the Bebop test suite. We'll focus right now on separable rastrogen because that's the one they were tuned on. Now, according to the objective function, the average number of evaluations, the graphical EA came out ahead by a pretty substantial margin. Now, not statistically significant, a t-test says 0.39 for the p-value, so very small difference. And that's because the median is so much higher. Despite having a lower average, it has a much higher median, and we'll look at that right now. So as you can see with this cumulative distribution, it's not until about the 95th percentile that the traditional EA starts to lag behind the graphical EA, right? It's doing substantially better than the graphical EA in 95% of cases, but these last 5% are so much worse, keeping in mind this is a logarithmic graph, that it manages to push up the average so significantly. And this is the same distribution, visualized differently, and yeah, you can kind of see why this would be the case. The graphical EA, notably, has an incredibly tight distribution here. So tight that we thought it was a bug, or we had forgotten to reset the optima in between runs, but no, that's correct. It has a distribution that tight, which is honestly kind of strange. That's not something you would expect from any EA, but that's just the evolved behavior. Now, they were tuned for separable rastrogen, but we also wanted to test the generality of these EAs. So intuitively, one would expect that the graphical EA would perform worse on other functions that they weren't tuned for as compared to the traditional EA, right? So the hypothesis there is that this freeform structure is allowing for optimization to a degree that a traditional optimizer just simply can't achieve, specializing to the specific characteristics of the problem at hand. But that would almost certainly come at the cost of its generality, in terms of being able to operate on other different functions that have nothing in common. And that is largely what we saw. We have the sphere function here, a very simple function. The traditional EA did much better than the graphical EA. Separable ellipsoid, the traditional EA did about an order of magnitude better. Rosenbrock, the traditional EA did terribly, but the graphical EA couldn't solve it a single time across 250 runs. Not once could it solve it. And that agrees with our intuition. But then we got to the step ellipsoid function and saw that the graphical EA blew the traditional EA out of the water comparatively. The p-value is about half of the p-value from separable rastrogen in these from t-tests, which is to say that in terms of the graphical EA's advantage over the traditional EA, there's about twice the advantage on this function they weren't tuned for as opposed to the one they were. And for context, these are about as different of functions that you could possibly have. Separable rastrogen is extremely multimodal. Step ellipsoid is unimodal. And it's also a staircase function. It's truncated. There's zero gradient. It's not a curve. These are about as different as possible. So we have no explanation for this, other than that there's probably some strange unknown dynamic here, or it's just a weird coincidence. So to recap what we've done here, we've come up with an EA representation that allows for a freeform mutable structure and has a much larger search space in terms of the representable EAs, and removes a lot of the human bias that you get from having a specific set-in-stone structure. We've shown that a meta-optimizer can take advantage of this structure to generate high-performance EAs that are competitive with traditional optimization techniques. And something we didn't have time to talk about today, but we did have a section about in our paper, is the ways in which a human can analyze the graphical EAs that you get from this process to try and find out new things about EAs in general. And in particular, we did find a specific structure that came up frequently, but that didn't really have an analog to existing techniques as far as we could find. But that would have been pretty easy to implement by hand if you wanted to. And that's the kind of thing that you can get out of this. You could find general, widely applicable things about EAs, novel techniques that aren't necessarily constrained specifically to our representation. In terms of improvements we could do for the future, well, just from the blue line on that one graph, we didn't really have time to talk about our mutation function, but you could tell it did poorly. Very, very poorly. We're probably just going to throw away everything we have and start from scratch and try to find something better. There's also some arbitrary structural constraints that we imposed. For example, every vertex had to have inputs and outputs, and that's not strictly the case. That doesn't have to be true. You can imagine a vertex with no outputs just acting as a black hole that kills everything that goes into it. We didn't think that would be good. We didn't think that would help the evolutionary process, and so we didn't allow for it. But, removing human bias is a big goal of this, so we might as well at least experiment with it. And we could try to find a better objective function than just simply using the average, and try to more closely align with human desired distributions. We don't like the odd scenario of, well, technically we beat iRace according to our objective function, but also iRace had a more desirable distribution that you might prefer in practice. We could build in a tolerance for outliers or something like that. And that's the end of the presentation. If you have any questions, please feel free to ask, or please email me at this address. I'll gladly talk all day about this. Thank you very much, and have a good day.